alaikum warahmatullahi wabarakatuh. Alhamdulillah. Wassalatu wassalamu ala Rasulullah. Amma ba'd. So, this is the third lecture in the lecture series of the steady state error. So, in this lecture, we will be discussing some terminologies, I mean the types of the system and how the steady state error behaves whenever we use different type of standard signals. In the previous lecture, we considered this closed loop system and we discussed the steady state error. So here just to recall the basic things what we did, we said that the steady state error will appear somehow in this format after some algebraic manipulations, and then if the unit step function is the input to the system, then it is easy to write down the error in this format. And this means because limit s tends to 0, g of s will be a constant number or value, so therefore there will be a bounded steady state error in the system in this case. So the error, the way we define the gain of the system, we define if g of s limit s tends to 0 and g 0. But this all theory, again, just to keep in your mind, will be applicable whenever the transfer function g of s has all of its poles in the left half s plane. As we discussed about the steady state error, just for the repetition and for recalling the basic concepts, we know that limit e of t tends to infinity is equal to ESS is the steady state whenever this closed loop is stable. So it will be the steady state error, and we can find out it by using the final value theorem. S tends to 0 S E of S. Now in this lecture we will be considering the standard input signals like a u of t, comma a r of t, the ramp signal, which we normally say is equal to a t u of t, and the parabolic signal a p of t, which normally we say a t square upon 2 into u of t. So this is the topic of today's lecture, that whenever we are using different type of standard signals, how the system steady state error behaves. Before going to study the steady state error behavior of the closed loop, it is better to get introduced with the basic terminologies associated with the transfer function in context of the steady state errors. So we will be discussing them now. So the transfer function we may write in this format, and to this we say pole 0 representation. It is not necessary to represent the transfer function in pole 0 format. The importance is the number of poles at the location 0 or at the origin. So we can rewrite the transfer function g of s in this format. So now g1s has no pole at the origin, while 1 over s to the power s minus s to the power n, these are the number of pure integrators. Like if we are writing n is equal to 3, this means there are 3 pure integrators associated with the transfer function g1s. So with g of s transfer function, so in that case the system behavior is changing and the steady state error behavior is changing because of the number of pure integrators in the open loop transfer function. To this whole thing, like g of s is the open loop transfer function. So in the open loop transfer function, number of pure integrators changes the behavior of the steady state error, and this is why we use some terminologies which are associated with the transfer function g of s in the context of the steady state error ESS. So here we look, the system will be type 0 system. We say the system is a type 0 system whenever n is equal to 0. Like if there is no integrator in the open loop transfer function, we say it is type 0. And then we say that if there is one integrator in the open loop system, this means n is equal to 1. This means there is one integrator in the open loop system. We say that it is type 1 system. Again, that whenever we have two integrators, pure integrators in the system, we say that it is type 2 system, and then type 3 and so on. So if there are n integrators, we say the system type is n. This means if there are 100 integrators, pure integrators in the loop, so we will say that the order of the type of the system is 100 type 100, you can say. So what is the importance of the type? Just one thing, if we can remember that if it is a type 0 system, the steady state error for the step input cannot be 0, but there will be some constant value of the steady state error. So these type of things we will be discussing in this lecture. So on this slide we will discuss the type 0 system in the unity feedback whenever input to the system is a step function. So the Laplace transform of the step function is a upon s. So the case type 0, we say that whenever the pure integrator, there is no pure integrator in the open loop transfer function. Like in this transfer function, if there is no open loop integrator, we say that it is type 0. So the gain of the open loop transfer function, whenever there is no integrator inside the transfer function, we can say that it is equal to a constant value, and that constant value is not equal to infinity. This means it will have some constant value, and if you want, we can say it, suppose it is c. So we write the steady state error in this format, and here we replace this by a constant c. Like over here it will be just a value c. So definitely this whole thing will be a constant value which is not equal to 0, and maybe this is equal to something c2. So whenever the value of g0 is increasing, the steady state error will be decreasing. Like suppose we consider g0 is equal to 9, then from this equation we can say that the steady state error will be a divided by 1 plus 9, which will be equal to 0.1a. And again, if we say that suppose g0 is equal to 99, then it will be equal to a divided by 1 plus 99, which will be equal to 0.01 a, and so on. So as the gain of the open loop transfer function is increasing, the steady state error is decreasing. But remember this fact that in some cases, whenever the gain of the open loop transfer function is increasing, the closed loop may become oscillatory, or in some cases it can become even unstable system. So conclusion of this discussion is that if the system is a type 0 system, then the steady state error for the step input will never reaches to 0. It can become small and small whenever you are increasing the gain of the open loop system. But if it is type 0 system, there will always be some steady state error. So here we say that the zero steady state error is not possible if the transfer function has no pure integrators in the open loop transfer function g of s. In this case, the steady state error is finite but not zero. Once again, the same system we are taking, like the input to the system is step input, but the type is type 1. And we understand now that whenever n is equal to 1, it will be type 1 system. This means that there is one integrator in the system, or one pole is at the origin. So here n is equal to 1. So in this case, the open loop transfer function limit this, so the gain will be equal to infinity. So if the gain is equal to infinity, g1s will be equal to infinity. Here we write the steady state error relationship as we discussed many times. We can write like this, and over here if we want, we can cancel this s with this s. So the total system can be rewritten like this. Now if s is equal to 0, so this means this portion is equal to 0, and definitely if this is s equal to this, if this 0, so this whole thing is infinity. So then infinity multiplied by g1 of 0, this whole thing will be infinity. So 1 plus infinity, so we will get infinity. So 1 over infinity is equal to 0. So from here we conclude that if the system type is 1 or greater than 1, and input to the system is unit step input, in that case the steady state error will be equal to 0 if the total closed loop is stable. So the conclusion is somewhat written like this: to track a step input with 0 steady state error, this means ESS equal to 0, the open loop transfer function g of s must have at least one pure integrator. This means a pole at the origin. So now we will discuss whenever the input to the system is a ramp function, and the system is type 0. Type 0, we know that in the transfer function there is no pure integrator. So the steady state error equation we can write like this, and here we know that this s we can cancel like this, and here it will be limit s tends to 0 a upon s plus s g of s. So if we take the upper limit and lower limit, so it will become a, and because this one is 0, this will be 0 plus 0. So this is because s is 0 and g 0, whatever the number is there, but here you will get 0, so it will be a upon 0. So the total thing will become infinity. It means that even if this closed loop is stable, but the input to the system is a ramp input, then the steady state error will diverge even if the closed loop is stable. So if someone is asking us to design the closed loop system in which the steady state error should be a constant, then it will not be a solution. So here cleanly written, somehow the same thing is typed over here. So now we discuss about the system. If the system become type 1 system, then what will happen for the steady state error in the closed loop. So here again we write this, the system is over here. So again, like E of S, we can write like this. We repeat the same equation over there. So if we simplify it, here we will be getting and this will be equal to limit S tends to 0 A upon S plus S G of S. So this will be limit S tends to 0 A upon S into plus S into 1 over S into G1S. So S will cancel with S, and because we are saying that S tends to 0, so it will be A upon 0 plus G1 0, and G1 0 will be a constant value. So this means A upon G1 0 will give us something constant value. So there will be a steady state bounded error in this case. So the summary of this analysis says that if this closed loop is stable closed loop and the open loop transfer function is type 1, then the steady state error for the ramp input will be some constant value. It cannot be reaches to 0. It can decrease whenever the gain of the open loop transfer function is high. Like for G1 0, if it is high gain, then the steady state error will be smaller. So the typed version for this discussion is over here. So you will get this, and of course here will be a constant value. This cannot reach to 0, but increasing the gain of G1 0, it can reduce this error. And again, like it is a repetition, but anyway, increasing the gain of the closed loop system in many cases can give the oscillatory response, or even the loop can become unstable. So in the design, one should be careful. The same ramp input, if the type of the open loop system is greater than or equal to 2, and we write the steady state error as we wrote in the previous equation, so it is somehow like this. And if we simplify it, this and this, so we will get S tends to 0 A upon S into 1 plus 1 over S to the power n G1S, and a little simplification will give us S tends to 0, and here we will have A upon S plus, here is this is a typographic error, here originally it will be G1 of S. So then we say S, so it will be 1 over S n minus 1 G1 S. So this will be 0, this component will reach to infinity, and this will be G1 0. So this whole thing will be A upon infinity. So in this case, the steady state error of the system will be equal to 0 if this closed loop is stable. And the summary is that if someone wants to design a closed loop such that the steady state error for the ramp input signal is 0, then the open loop transfer function must be type 2 or higher than type 2. So here the type version of this discussion is, so we can write like this, and this will be equal to, of course, 0. So type 2 or greater than 2 system accomplishes tracking of a ramp input system, that is the steady state error will be equal to 0. So once again the signal input to the system is the parabolic signal now. Before we tried with the ramp and step. So if it is a parabolic signal, what will happen to the steady state error? So we look to the type 0 system. So in the type 0 system, again we can write like this. So here if we do the simplification, so this will cancel and here we will get square. So it will be equal to limit s tends to 0 a upon s square plus s square g of s, and definitely it will be a upon 0. So this is infinity. This means that if this closed loop is stable and the open loop transfer function is a type 1, type 0, even then the steady state error of the system will diverge. So the type version of the system is somewhat like this. Again, if we look for the type 1 system, that is there is one integrator, then again ESS, we can write this, rewrite this equation over here. So again the simplification of the problem will give us somehow this result, limit s tends to 0, it will be a upon s square plus s square g of s, which will be equal to limit s tends to 0 a upon s square plus s square into 1 over s into g1s. So this we cancel here. So this will be equal to limit s tends to 0 a upon s square plus s g of s, which will be equal to a upon 0. So once again the steady state error will diverge even if the closed loop is stable. So the conclusion for this discussion is that if the input is the parabolic input and the closed loop is type 1, even if the open loop transfer function is type 1 and the closed loop is, even if it is stable, the steady state error of the system will diverge. So the designer should be careful in such cases. So the type version is somehow like this. Now for the parabolic input, if the open loop transfer function of the system is type 2, then once again the steady state error we can write like this, and these calculations are straightforward. We did them the similar thing many times. So you will have limit s tends to 0 a upon s square plus s square g of s, and then we can write limit s tends to 0 a upon s square into plus s square into 1 over s square into g of s. So these two will cancel, and here you will get limit s tends to 0 a upon s square plus g 1 of s. Here it is g1s. So you will get a upon g1 0. So g1 0 is a constant value, bounded value. So we will get the steady state error like ESS will be equal to A divided by G10, which will be some constant value, and it will be a constant value. This means that increasing the gain of G10 will decrease the steady state error, but it will never reach to 0 whenever the input at the set point is a or the reference input to the system is a parabolic function parabolic signal. So the type version is written here. So we will look that whenever the type is greater than or equal to 3. So in this case, again the figure, I think I have given the number later on like this one. So over here, if you do the calculations, at the end we will get this relationship, and here if s is equal to like 0, so this whole thing will become infinity. So we will have 1 over infinity, so the steady state error will be 0. This means like if the type is greater than or equal to 3 for the input reference signal, a parabolic signal, then the steady state error of the closed loop will be 0 if the closed loop is stable. So the conclusion, for type n greater than or equal to 3, so such type system can accomplish the tracking of a parabolic input, that is the steady state error will be equal to 0. So the steady state error summary of the discussion, like if input is the step input, here it is written like it is equal to 1 hour, a hour, as then for type 0 system the steady state error is constant, and for the type greater than or equal to 1 there will be 0 errors whenever we give the input as a ramp function. So this is, you know, that this is in time domain a u of t, and this one is a t u of t, and this one is a t square upon 2 into u of t. So this is what happens here. We see that it is a, if I write in the polynomial format, like suppose the input signal to the system is say r of t is the signal, and suppose this signal is a plus maybe a0 a1t plus a1 a2 t square plus so on plus an tn whole u of t. Suppose this is an input signal. So to get the steady state error equal to 0, the type of the system should be greater than n. This means the type should be n plus 1 or greater than that. Then the steady state error will be 0 if the closed loop is stable, and it will be constant if the system type is n. If the type of the system is less than the degree of the input signal, then the steady state error will always diverge, even if the closed loop is stable. Here we will discuss one example. In this example, like the input signals are 3 types, like step type of signal, and the ramp type of signal, and the parabolic signal, and the system is here. So if we see there is no pure integrator, this means it is type 0 system. So for 5 u of t input signal, if we give and the closed loop is stable, then there will be a constant steady state error. But for the other two signals, the steady state error will be infinity. So over here g of s is equal to this. So the closed loop transfer function first we should write. So the closed loop transfer function t of s is equal to g of s upon 1 plus g of s. And now if we insert these values over here, so we will get 120 s plus 2 upon 120 s plus 2 plus s plus 3 into s plus 4, and then a little simplification of this will be giving us 120s plus 240 upon, from these two we'll get s square, and then it will be 7 plus 120, so 127 s, and then 240 plus 12, so 240 plus 12 will be 252. So first we should see that whether this is a stable transfer function or not, and you can use over there the Routh-Hurwitz criterion to find out the stability of the system. So you know it anyway, so we can write like this the parameter. So here it will be what, 1 252, and here we will have 127, here it is 0, then this is positive number, this one is positive number, and then we will write over here like minus 1 127 252 and 0 upon 127. So this simplification is given us 252 over here. So definitely this is positive, this is positive, this is positive. This means this closed loop is a stable closed loop system. So we can consider now that for the first one, for phi of t, there will be a constant value of the steady state error, and for the other two, it will, and the steady state error will diverge. So on the previous slide, we show that this is a stable transfer function, and then using the standard steady state error equation, we can put the things in this one, and here the steady state error will be this. If you put here s equal to 0, so this is 0, this is 0, this is 0, so 120 multiplied by 2 will be 240, and here you get 12. So simplification gives us this is the steady state error. For the other two signals, we know in advance that the steady state error will be infinity, but if you want to calculate them, so the procedure is simple. Just again we can write the equation in this format, and it is equal to infinity. Similarly for the other system, it will be again with this equation. You can put the values and calculate them, and you get the infinity over here. Then there are some examples that if you have understood the material, then you should be able to get the solution of these two examples. Try them, and if you can come up with a solution, this means you understood the material in this lecture. But if you are facing some difficulties, you must have to go through the lecture again and also read the material from the textbook. And you know that our textbook for this course is the Control System Engineering, written by Dr. Norman Noyce. So thank you very much for listening to the lecture.